So I want to do a video about something that particularly confused me when I was first taking signals and systems. In my signals and systems class, they brought up this function called the Dirac delta function. And they defined this function in the following way. They said that the Dirac delta function is equal to infinity when x is equal to 0, and it's equal to 0 when x does not equal to 0. And in a graph, they'd notate it in the following way. They'd say that, if this is our x and y axis, that should be a x, not a t, that when x is equal to 0, it shows just an arrow indicating that this blows off into infinity. And for all other values of x, it's just 0 on the x-axis. And that all seemed okay. I was able to stomach that as a student. What I really took issue with was this next statement, is they said that the area underneath this curve here is equal to 1. So let me just, actually that's worth writing down, that really this just means the area underneath this curve over here is equal to 1. And I thought to myself, why should something with an infinitesimally small width and an infinite height miraculously, have an integral who evaluates to 1? And that's the point of this video. It's to illustrate why these statements are true. And to do that, let's go over to something that I've prepared beforehand. So if you've taken probability and statistics, this should look very familiar. Over here to the left, I've literally copy and pasted from Wikipedia the definition for the normal distribution, or the Gaussian distribution. And from probability and statistics, it's very well known that the area underneath the Gaussian distribution, or the normal distribution, is equal to 1. And really what I'm going to assert is that the Dirac delta function is the normal distribution with a few caveats. And if I can show that the Dirac delta function really is just the normal distribution, then the statement that the area underneath the Dirac delta function is equal to 1 is because the area underneath the normal distribution is equal to 1. So let me show you why the Dirac delta function is really just the normal distribution in disguise. And really, here I have some values that we can manipulate for, inside the definition of the normal distribution. So you'll see if I change the value of mu here, that this value will, essentially the hump of the normal distribution will slide. I'm going to set that back to 0. You'll see why here in a few seconds. And I'm going to also assert that that sigma, when we're looking at the Dirac delta function, is actually just approaching 0. So, and I want to repeat that because this is really important, that really the Dirac delta function is the normal distribution with the caveat that mu is equal to 0 and sigma, the standard deviation, is approaching 0 from the right side. And we can see graphically and kind of visually that as I take this value of sigma and I bring it closer and closer to 0, that the normal distribution here, the height of the normal distribution, starts to get higher and higher. And what we're also going to see is that this width here is going to get smaller and smaller, right? And you'll see that as I keep decreasing sigma, that this starts to look closer and closer to what the Dirac delta function is, right? It's infinity when x is equal to 0, and it is 0 everywhere else. So really, that's the intuition for why the Dirac delta function is 0 when x does not equal 0, and when it's infinity when x is equal to 0. In the next video, I'm actually going to show that, regardless of what value we have for sigma, that the area underneath this curve when mu is equal to 0 is equal to 1. And therefore, that I will prove that the area underneath the Dirac delta function is 1. See you in the next video.